Yeah. So great to be here. We have 2 microphones, which is not quite adequate for everybody, but it'll work. What you see in front of you is a bunch of kids. I've known these guys since they were kids. We were all working on AI back a long time ago, and so you've got oh, that's great. You've got hundreds of years of experience with AI here, and I'm not sure if I have to give introductions to them, but I'll just say that you know, Peter wrote the book. Scott Penberthy was doing qualitative reasoning research in the 80s and runs applied AI at Google. And Gumby, we call David Henkel-Wallace. He's started several companies and is now trying to recreate some of Marvin Minsky's K-line work. And Ken Haase has made all sorts of systems forever. So enough of that. The modern AI ecosystem is really starts with some standard computer science. We create languages that render problems trivial, prototype to test abstractions, debug and maintain to test for what we know we'll use it for. But actually, programs are always changing or else they die. And that's, Alan Perlis said that, organisms or those things. And the question is, what techniques do we use for what? And you know, there's been, from the beginning of AI, actually, you know, in the 40s, Hebb wrote a book about neural nets. It's not a brand new idea, but we've been using, you know, things about, you know, rules and forward chaining and backward chaining and frame systems and truth maintenance systems and simulation and HMMs and SFVMs and random forests and DNNs and RNNs and CNNs and adversarial networks. The question is, as we're using all these things, do we really know what we're using? Do we know how to debug them? Are we using too complex of things? It's hard to know. So many tools. We're all learning PyTorch and TensorFlow and CNTK and OpenMind is around. I don't know if any of you guys use it, but a couple of us have, and Theranos and Keras. What I enjoyed about this picture on the right is in a training video of Microsoft, they show this beautiful graphical representation of a recursive neural network. And they show this beautiful, on the top, symbolic description of it. And then they show how, you know, a few years ago, if you take a look at this old TensorFlow code, it wasn't so pretty. And so I'm kind of enthusiastic about how things might be getting simpler and better. And certainly when we're looking at problems, we try to understand them beforehand, and we eyeball them, as our friend John Lamping will talk about. And runtime analytics are a great way to look at things when we're debugging things. And TensorBoard, these 2 pictures at the top are from TensorBoard, which recently they made it so you could actually program it yourself pretty easily. And this next picture is from a program I wrote to look at structure of Bayesian networks, a multi-fisheye view approach. And this bottom one is another system I built, a context builder, where we graphically snap things together to make an AI system. So I think that graphical techniques are exciting and will be part of life. But today I just want to start by finding out what these guys have learned over their lifetimes. And I just want to start with each of you taking a moment to tell me about something that you made or debugged that made you think about AI tools. And so I don't know, maybe we'll start at your end.
Okay. I guess to me, what I've learned most is that trying to understand the data is where everything starts. And I feel like you know, you come up with an approach, you figure out what you're trying to do, and the tools we have are mostly focused on programming, right? So we've got 50 years or so of an industry where we have good tools for programming now. We have source control systems, we have unit test frameworks, and so on. And we've made it continually harder and harder to put a bug into a line of code. You used to be able to pass the wrong type to a function. Now it will tell you at compile time that that's not allowable. But with AI and machine learning, we're shifting our focus to the data rather than to the code, and we don't have 50 years worth of tools to do that. And so I think that's what what we need to focus on in the next decades is can we do that? And you know, there's all sorts of stories of places where the data was just wrong. And I think when you're in a big company, you probably see that more than when you're in a startup. So I can think of half a dozen times when teams have said, okay, we need this data product. Oh, great, somebody else is producing it. Let's see if that works. Load it in, it works great. I think my problem's over. And then a couple of months later, things just start to get worse. And the reason is because the other team that was producing that data, they weren't really doing it for you. They were doing it for themselves. And their goals changed, and so the data changed a little bit, and it got better for them, and it got worse for you. And we don't really have the tools to track that. And so that's kind of what I've been focusing on, is can we come up with a set of tools and a set of ways of thinking that's saying maybe the problem is in our data, it's not in our code. One of my hobbies is to track cases where major companies have outages. You know, Google goes down or Facebook goes down for an hour or whatever. And it's very rarely the case once you see the analysis that somebody made a mistake in the code. It's much more often it's in a configuration file, or you know, there was a DNS entry that was wrong and that got propagated. And the reason is because we don't have these strong type checking code for our data. They're just bytes of data. And so that's what I've been focusing my work on, is trying to build that set of tools set up.
When I was doing my PhD thesis, part of it was a system for trying to invent programs that describe mathematical concepts. It was a rational reconstruction of this program called AM that Doug Lenat had made at Stanford. And it worked by having a combinator language, and it explored combinations of those in order to see what kinds of functions they computed. And at one point, because my master's thesis had been about type specification inference, I came up with this great type checking algorithm. And I immediately put it in so that it only created programs that were valid type-wise. And immediately, it failed to produce many of the inventions or discoveries or whatever you want to call them that it did originally. And the reason for that is that a lot of those things come in places where a function is well defined for one part of the domain, but not defined for the other, and those were being excluded by this type checking. Now, when I did it, a lot of my colleagues at MIT sort of gleefully said, well, that shows you why strongly typed languages are for uncreative people. And I actually didn't buy that, but I took instead the lesson that when we create these complex systems, there are going to be components that aren't necessarily well behaved. And what we need to think about is how those fit together and how they define a logic of their own. And it turns out that some of those domains defined by when something produces an error and when something doesn't are in fact useful real distinctions. And so thinking about how you organize systems of these models or representations or components is a key thing. And that's something that I learned, and a lot of what I've been doing for the rest of my career is coming up with ways to create those systems and glue those things together.
So when I first talked to Ted about this panel, I was thinking of debugging, right? Running a debugger on a piece of code. But you know, talking with Peter about this, I started to realize that my approach to thinking about AI problem domains is really it's more akin to very complex hybrid systems, whether they're big distributed network systems or societies where we don't really have a way to debug the entire thing. And so when you do have, you have to start thinking about the problem in a different way. And so one of the nice things about when you have a bug in a complex AI system is that it's usually extremely funny. Like Ken's example, or actually when I was working for Doug Lenat that Ken mentioned, we had a system that was representing psych, that was representing human knowledge, and we asked it, could Archimedes have discussed science with Einstein? And the system was, yeah, of course they could have. And why is that? Well, we know when those people were alive, but the system, no one had told the system that spans of time must be continuous. So obviously it made sense that we only know a certain amount of Archimedes' life, and perhaps he spent part of it in the 20th century. And you know, the interesting thing about when I was thinking about that bug is that debugging that bug involved understanding the logic and the data that the system used to make the analysis. And so in modern systems, modern AI systems, one of the hard problems, DARPA has been funding research in this area, is explanation of systems. And I realized that explanation and debugging are actually, in the AI domain, are really the same problem. Because you really need to look at the entire problem holistically. You can't just put a breakpoint in your code and say, oh, I got the wrong sense in this if statement. So my recent work has focused on marrying symbolic systems to neural networks, because you can use the symbolic system to extract the semantics of what's going on in the neural network. And we're going to talk about that a little further.
So we're at question number 1, is that right,
We're trying
Ted?
to stay on question number 1, but
So I gotta stay on
people
number
are
1?
slipping down the.
So had people in here written C++ before? Anybody? Show of hands.
There we go.
There we go. How about Java? So do you guys like waiting for the compile? Hate it, right? So I got into AI. I learned from Peter many years ago at MIT, and I didn't believe neural networks either. And in 2012, started playing with these things, because you see ImageNet, like, how's this actually working? And you look at it, and it's all math. And then I learned very quickly, I said, oh, it's Python. This is cool. There's like no compile. It's going to fly. And then there's this thing called training. Has anyone ever trained a neural network before, a big one? Pain in the neck, right? I mean, this takes forever. So I said, well, how do you make it faster? So I started asking Googlers. And they said, oh, no. Just use containers. And you do it on Borg and get as much as you possibly can and ask for a whole TPU pod, which is a supercomputer. So I wired this whole thing up. And sure enough, I got a training system in Python, and I was training it on a pedagogical problem of a self-driving car. And so I had about hours of these self-driving car images, and I was training a CNN to identify from images, turn left or right, and then throttle. And I had this. So I do distributed training, and I had these different parameter servers that basically hold the parameters, and you had workers that would actually try a few images and send them back. And you build this distributed system. So I built the whole thing. It's all running. I tested every component, did all the things right, Ted. I thought it all runs great. I start it. An hour goes by. 2 hours go by, add more nodes, 2,000 nodes, keeps cranking. I'm all set. I go away, have lunch, come back, it's still running. Go to bed, wake up, still running. I said, great, it's got 4% left. The thing stops. Shit. It's sitting there, and I spent a day and a half, and the teacher's like, well, when are you going to turn this in? I was going to retrain it. So I started again. And I said, well, I must have done something wrong. I do all the unit tests are fine, system tests are fine, everything passes, run the whole thing. Start running again. I'm running on containers, the latest from Google. It runs for a day, 2 days, a little long. Oh, it's almost done. 90% stops. And it was due yesterday. And I couldn't figure out what's going on. And so realized that the new compile is the train, is now training, and we're very impatient, so we want these tools. And I was using containers. It took me an entire weekend to find it. And what had happened, Ted, is under the covers of all the containers, you have a parameter server that talks to a worker server. And there was a new security patch that was just released that I didn't pay attention to. And a security patch said, well, we got to change the random number algorithm that generates the ports when you first do a random TCP connection. And so what happened is it changed it would reset after a while. It would reboot a container that failed. It would change the port number, and that would propagate, and my parameter server would lose every single thing. So it was confusing because all the computers were pegged. They were all doing all their work, but I couldn't see it because of a low-level security patch that I wasn't paying attention to that changed the random number for the port. So I guess the point here is that these systems are highly complex. And the training's a new hard issue. And I found that the tools to inspect this stuff were just missing. You know, how do you go look at a worker? How do you pull the data out? And I have some more tools we can talk about later. But that was just one example of, had this huge complex system, was all excited using the latest and greatest supercomputer, and it was a random number generator for a port in a TCP connection that brought the whole thing down.
So in some sense, we have systems that have lots of parts, and if we don't, the parts that we don't model, we don't understand. And I guess my next question was to be, and we don't have to take too long on any of these, is what's different about AI programming than other programming? And I think you touched on that a bit. Maybe somebody could hand him a microphone though. But I think it's an important question. I mean, maybe it isn't any different, but certainly the data thing, and there's a lot of different aspects.
Yeah, I think that's part of it. I think you're right. I think that both software engineering and AI are about making programs that do the right thing. And the two differences are, one is what is the enemy? I think in regular software engineering, the enemy is complexity. And we have tools for breaking down complexity into subcomponents and so on. And in AI, we're really focused on uncertainty. In regular programming, we try to make the uncertainty go away. And in AI, we say, well, that's the whole point. That's what we're focused on. And that's what the hard part is going to be. And so we're dealing with probabilities rather than logic, rather than having, you know, defining an ontology of classes of objects. We say we're just going to have a bunch of weights in our neural network, and there won't be strict boundaries between classes. So it's a different way of looking at the problem. And then I think the other thing is, what's your success criteria? What are you trying to do? And in regular programming, you're trying to kind of prove your programs correct. You have a mathematical specification. And of course, we never actually prove them for anything longer than the 5-line little examples. But we come close to doing that. We write unit tests and we say, for all these tests, it satisfies these properties. And in AI, it's not so much that we say what the specification is, but we say, here's what we want. Here's a goal that we're trying to maximize. And so we're not telling the computer how to do it, we're telling it what we want. And I think that one reason why we haven't made the progress we hope we can make is we're just not that good at that yet. And I think as a society, you know, we have all our legends are about not being very good at saying what it is that we want, right? We have like King Midas. He was asked for a software specification of what he wanted, and he said, everything I touch should turn to gold. And then he found out there was a bug in that specification, right? But he could have done better, right? So we don't have all the practices yet, but we have some good practices, right? If King Midas had only said, I want everything I touch to turn to gold, but I want an undo button, and I want to pause and resume, all right? He would have been okay then, right? And so there are some things we know for how to better deal with explaining what it is, what we want, but it's hard. It's hard to get it right. And that's true just for an individual. Just think how much harder it is to do that for a society. And look at all the issues we have today, where half of society wants to go in one direction and half want to go in an almost opposite direction. And how do we reconcile that? And so I think that's the challenge for AI.
Ages ago, when I was an undergraduate, I dropped out of MIT for a little bit over a year to work at Atari. That's actually when I met Ted. And one of the things I did then was I organized a conference on AI and character animation. And one of the people who came there was Craig Reynolds, who had built the computer animation system at III, which was used for the first Tron movie, which was back in the 80s, for those of you who have only seen the second one. And Craig came up and he talked about his program. And he said, well, actually, my program isn't an AI program. It's just a big Lisp program that usually works. And Alan Kay was there, and he said, well, isn't that the definition of an AI program? And I think that one of the ways in which AI is different from other kinds of programming along the lines that Peter was talking about is that the specification is more complicated because it has these elements of uncertainty in it. I think another reason that it's different is that a lot of AI programs have representations in them that capture regularities in one way or another, whether it's regularities in a distribution, which get built into the representations that are implicit in a set of weights, whether or not it's a representation which is set up in a knowledge base. And those representations tend to be a lot richer than the representations which we usually create in the software we have. And there's a big issue when you're trying to connect complicated representations with each other, is that it makes it possible to, for instance, have puns and jokes and things like that. And that's what makes part of the simulation or reasoning or debugging of these complex systems difficult.
So I actually use unit testing, standard unit testing in the Rodin system I'm working on. And you know, part of the issue here is you train a system on a data set, and you really can only make assertions closed over that data set. But of course, your implication is you're going to run it on an arbitrary data stream. So you've got a model of, if I've trained it on all of this set, I've trained a facial recognition system on this set of faces, this set of images. I believe that these set of images ought to work and these images might not work. And I got the way of sort of trying to apply inductive reasoning to my models. I hate to do it, but by thinking about humans. And there's always terrible, you know, of course, AI, humans, that leads you to make a lot of improper assumptions. But in this case, you know, if you want to work with someone and you want to get them to operate a piece of machinery, for example, then you instruct them and then you essentially do some unit tests on them, right? You say, so we're going to pull the lever with a red knob on it, and they nod or they don't nod. Or they say, do you know which one I'm talking about? And you have these iterative tests you give to people to believe that you've put the same states inside their heads that you have in your own head. And then you say things like, okay, so now go try it and I will watch you. It's canonical Boy Scout kind of training kind of thing. And so my unit tests are not structured by your usual unit test. You know, parse this string and you should throw an error, you know, you should throw a condition based on, you know, such as this. No, there are, I've given you some data that you were not trained on. Are you going to properly induce what I want? And this is not so much a debugging technique, I suppose, as it's a verification technique, but it's a way that we can use existing tools that we've already got to take advantage of infrastructure we've already got to at least marshal the AI tool in the direction we want to go. So this is something about what's the same about AI and other programming.
Yes, I'll use this one.
This one's, I've warmed this one up for you.
Is the AI
it's been
mic.
trained already.
Yeah, this has got really cool stuff in it.
Use both, you know.
So both? I could do a double mic. So what's different? I think AI, the kind of AI that neural networks and that sort of programming computational graphs, it's much more like parenting than it is by programming. In a sense, if you think of a lot of AI traditionally growing, a lot of stuff that Peter has, we've talked about here, it's, you know, list representations and symbolic reasoning, really extremely clever programming techniques, right? And the A-star search is fundamental to chess. So really interesting graph search and other algorithms. What I find different about neural networks and computational graphs is it's more parenting. What I mean by that is one is that you're framing the problem as an optimization problem or as a generation problem. And you're trying to reframe traditional things like caching. You know, in other words, you know, like fundamental problems in computer science, caching and naming and predicting what's going to be next on the web page. You frame these prediction problems first. The next thing you have to do is how do you frame the input as a tensor? So we're used to data structures as, you know, linked lists and trees and whatnot. Now it's a tensor, which is a strip of numbers, or a strip of numbers in a square or some other with a surface normal, but it's a strip of numbers. You train the output as another tensor, and then it's a matter of plowing through archive and thousands of research papers and figuring out which computational graph is best to use and then which technique for optimization. And the parenting piece is, you know, framing the problem correctly for the child, feeding it appropriately, making sure you're coaching it with a good optimization, a cost function, because be careful what you ask for, because you'll get it. And then over time, making sure it's in an appropriate environment so it can learn and adapt. And so in that sense, it's a lot different than programming as when I grew up.
Yeah. What I really like about that question is it's leading into what we're going to talk about later with the representation business. And I think the next thing I wanted to get you guys to focus on is, these days it's grab all these tools that you can find in libraries and everybody else's examples and go. Is that better or worse than writing it from the bottom, from the basement by yourself?
I think that's certainly true. A good summary of where we are today. I don't think that's really specific to AI in any way. I think that's true across programming. Hal Abelson says we've changed computer science from mathematical science, like I was talking about trying to prove your program is correct, to natural science, right? So you're like a biologist saying, well, I observed this species, this program here, and I have some theories about how it works, and I have a field manual, or the manual for the program, and some of what it says in the manual is right, and some of it's wrong, and so I have to do experiments, and I never really understand the program. I don't read the code to the level where I can prove it correct, but I say I think its behavior is such and such. Let's do an experiment, see if that's what the behavior really is. When I'm comfortable that the experiments work, then I move on to the next piece, right? So it's a different mindset. It's the mindset of a scientist rather than of a mathematician.
So we've got a parent and a scientist.
I've started using the phrase deep stack for developers who understand the pieces, but they also understand something about what's going on inside them, sort of some understanding of what's going on inside databases, not just how to write SQL, some understanding of what's going on inside a compiler or a runtime or a file system or all those kinds of things. And it turns out those things do help, because when things go wrong, sometimes they're happening inside a module, sometimes or inside a component, but sometimes they're at the intersections between components. I think that one of the things that's important to keep in mind when we create these things, these assemblies, is that there's really two kinds of debugging. There's debugging in order to figure out what a module is doing wrong or what it's doing at all. And there's debugging in terms of the interactions between the modules, the things that I talked about as puns or jokes or just inconsistencies. And it may be that those different kinds of programming require different kinds of tools, and they certainly require different kinds of skill sets, because you're looking at a bigger picture rather than a smaller picture. You're looking at logs and doing git splits rather than running GDB. And I think we need to think about both of those as we create these kinds of systems.
He has one.
You guys are so generous.
Well, for the reason that Peter or Hal correctly identified, I hate using other people's code, but I'd never get anything done if I didn't. And the reason is I don't trust other people's code, and I expect that the users of my code won't trust me. And this is sort of going back to the same reason I was saying when we train a coworker on a tool, or your child on how to hold a pencil. You're like, yeah, I never know. They're not going to stab me in the leg with a pencil. But I have some iterative process, and I have some defensive mechanisms, right? With the feral cat, I kind of stay out of reach. And it's interesting that we've evolved a set of tools for that as well. Containers are a way of bounding variability. I was just talking this morning with a friend who's being screwed by his development tools, and he's just decided to put his entire build stack in a container, and so that it won't change, and it's frozen, and you can put your training down. And the nice thing is container is protecting both ways, right? If something inside decides to dereference a null pointer or read some random pointer, it hopefully can escape the container, and vice versa. Your code is hermetically protected. The downside is you really have no idea what's going on under the hood. I think AI systems give you more resilience on that front because they are all about emergent behavior. So even if the thing malfunctions, the library you're using isn't actually operating the way you expect, if it's at least consistent, your system might actually operate in a consistent and therefore usable fashion. Not a very positive view of the world, but I think it's realistic.
So I think we're living the day of the great impatience, right? In the sense that we can go onto Facebook and create a page in a few minutes. You can use Square and whip up as someone not knowing anything about computers and have a little store up and running in no time. So why should code take any time at all to write? Because I built a website just this afternoon. So why is your stuff taking so long? And so we have this pressure on developers to go get and pack things together as fast as you can. And what I'm seeing is in this environment, sometimes it helps just to slow down and pause a bit. Because I was working on KubeCon. You guys know what KubeCon is? It's a conference about Kubernetes and containers. And there's a team working on Kubeflow, and I was part of that team, and we wanted to do a demo. And so that's AI on top of, it's like the latest stuff complete, in the sense of AI on top of containers, on top of Kubeflow, everything. And so we were all excited, and we were planning really far ahead, and we had this, attention networks, which is the hot thing, a transformer network. It's a kitchen sink of AI networks. And they said, well, we're going to do sentiment analysis as a demo of Kubeflow. And they said, well, we're not going to use just the 20,000 standard things you see for movie reviews. We're going to take all of Wikipedia. And so they said, more data, more algorithms, more compute, throw containers. And this thing is running 4 or 5 days. And we're looking at the time, and like, we're out of time for the demo. And we couldn't get it to converge fast enough. And the transformer was breaking, and the tools to inspect it were terrible. The tools to look at, do you have the right distribution of data were terrible. We couldn't look at embed, nothing was there. And we're doing print statements. And finally we stood back and said, we have no time. And we looked at the problem again and said, let's just tear it up, start from scratch. And by going back to first principles and thinking about the problem, we reframed it, wrote some good old-fashioned Python from scratch without libraries, and we had the thing running about 4 hours. Right? And I think what I see this is a lot in young programmers, especially coming out, is that they find the latest tool, they read about an archive, there's this pressure of the great impatience to get something done, and they go after and use the latest tool, assuming that's what I need, but the tools to debug that, understand it, are impoverished today for tensor calculus. And it's almost like, how can you teach someone to get the fastest result? Take a few minutes, don't just Google and cut and paste. Like great programmers copy, amazing programmers paste, right? So can you take a step back before you even begin that and think about the problem from first principles? And I think it's going to help a lot of us.
So in a lot of these stories, there's this question of knowing what you're looking at. I don't know, visualization isn't just graphical, but I think understanding and seeing what's wrong in a problem like that and having, finally punting. I mean, that in some sense, you weren't able to understand how these transformers are working. So what do you guys think about what are the best ways, or what are ways that you'd like us to see us going about visualizing your work as you're doing it and afterwards and as you're debugging?
So I remember Jeff Hinton was asked, how can you possibly visualize a million dimension space of data? And he says, oh, it's very easy. You just project it down to 2 dimensions, and you stare at it, and then you say to yourself the word million very convincingly. And I think that's what the state of the art is, right? So our vision system isn't going to invent any more dimensions than 2. And we can put on a headset and fake having a third, but going from 2 to 3 isn't getting you very much closer to a million. So I think I don't know if visualization is really the right word. Okay. I would rather say we want understanding and analysis, right? And there's always 2 tasks you have. You want to make your system better, optimize it, improve it, get better accuracy or whatever, and you want to understand it. And sometimes you want to do both of those. Sometimes it's okay to say, well, I made it better, and I'm not sure exactly why. I don't really understand it, but we're at 99%, and that's good enough. Move on to the next problem. And sometimes you say, well, I really do have to understand it because I need to be able to convince myself that I'm not going to have problems down the road when the world changes. And in order to do that, I have to really get an understanding of what's going on and where it's going to break down. And so that visualizing it is part of it, proving it correct is part of it, having a lot of tests, putting it in a lot of situations. You know, that's where we are.
Ted, just to break protocol, could I ask you a question?
Sure.
So you mentioned earlier about being a scientist, right, and how it's evolving in science. And that just dawned on me as I'm listening to you, because think about these complex systems of a million dimensions. So what scientists do is all the time with DNA, right? And the tools to treat computing as a real hardcore science, maybe they don't exist. You know, control set and a test set, and you know, the tools of inspection of a biologist and a chemist, we don't have in computer science, because you can't possibly know every single DNA how the strands work. So any thoughts there, Peter, about going back to your thought about being a scientist, what kind of things would we need as a scientist now than a mathematician if computer science evolves to being much more of a science than mathematics?
Yeah, I don't know. I guess I don't know enough about what the people in genomics do.
Or in chemistry or physics or experimental physics. You know?
Yeah.
Well, having worked in that field.
Okay. You asked the wrong person.
Yeah, I'm again, I'm violating protocol, Ken. I hope you'll apologize, Ken, I'm violating protocol here. I actually hate these visualization tools, with one exception.
Not a fan of T-SNE? You don't like that?
You know what's great about these tools? They make great demos for people who don't yet understand what you're actually doing. So, you know, the symbolic system, you grow a bunch of nodes, they have a density.
Draw a graph, right?
They got density of attachment. Well, actually, you can just going back to the previous question, you can just download a force-directed graph widget from Node, and you get these beautiful dandelion charts, and, you know, they're very exciting, and they look like they are really informative. They turn out to be completely worthless for debugging. I already know there's a lot of attention on you know, worrying about moving the robot arm where it doesn't move anymore, and procedures for recovering from that. I know that because I've watched it, and there's just a whole cluster of important schemes around that area. So seeing that on a graph provides no insight. Likewise for DNA, you know, actually DNA is a great example. The visualization of DNA and understanding that it's a helix through crystallography, which is, of course, not the frozen structure that's actually operating inside your body. It's just an example. That was very insightful, and it explained why that molecule works, certain elements of how that molecule works. But it only explains certain ones, and nobody looks at those crystallographic pictures to do any kind of genomics, because it answered one tiny question in a huge scheme. And the huge scheme's at such a semantically higher level that those kinds of visualizations were useful and then worthless. And you know, we know so little about those systems that the visualizations we have are really just this kind of probing. Do I believe that the protein conforms in this particular way? Let me sample a whole bunch of them and see that statistically that's true or that's not true. And that's the closest you can get for your AI system as well.
But another thing with genomics is what you do is you slice it up into small pieces. Right, you look at patterns and see how they compare.
Divide and conquer.
You look at that. That's right. Exactly. You know, you look at it's scoping.
But I would love that. I mean, there's no slideshow that I've seen for taking a slice of a neural network and looking at it, right? Or taking.
Oh, absolutely, there is. These guys run these gels, and you look at these patterns, and you.
Did you have a picture?
In computing?
You had that picture actually, very similar to one of those gel slides.
I do it. So, Ken, you wanted to say something?
I actually have to say something about the visual bias and the optical bias in your question.
Oh.
And one of my favorite lines of Marvin Minsky's is that if you only have one representation of something, it's a bad one. And that a lot of what you need to actually understand things is to have multiple representations. Yep. And visualization tools are giving you an alternate representation of what you've thought of as data or code or whatever. And that's important, but it's important also that the representations highlight and elide different things. as you're looking at it and as you're comparing it and as you're coordinating things from multiple angles.
So, well, how do you debug and test your complex big data systems? It's kind of a repeat, but it's
well, I actually wanted to answer that question in my answer to question 4, but I, having
held
strayed off the you know the path before, because instead of visualizing, you know, a lot of my early work was on the list machine, and the list machine, you've always got an interpreter available, so you write subroutines in the debugger to investigate and unpack data structures. And I find that, you know, now you have to write them ahead of time and compile them into your program with current debuggers. But, you know, instead of a visualization tool, you know, I write tools that ask it, you know, you know, where's been the focus of your activity? Where's the focus of your attention? You know, do I have a sheer large percentage of volume in this area, and is that the area I expect to have? And those kinds of questions can get compiled into unit tests, like I said, to at least assure repeatability. But even then, you know, I often don't have a good model of what a large amount of the data is. So these are still only scratching at the surface. If visualization just sort of gives you the vaguest view, I think these interactive tools give you a slightly better tool. They give you deeper insight, so they give you deeper ability to stick your fingers in deeper, but you still need the insight yourself. And when you have a huge raw data stream like these Google guys have to deal with, even those tools fail for me. But they're way better than visualization tools in my mind.
somebody else?
So maybe just talk about some of these larger, big, complex systems today. So if you think of, I guess, what drives the core of Google and other companies like that, today they basically have these data pipelines internally, much like we had in the 80s and 90s. They installed these things for ERP systems, right? You could finally digitize your goods, and you have supply, and you could see a whole supply chain. Now we do it for data, and the tools, we're creating them as we need them. And it's everything from moving your mouse on a screen to your interaction at a store or whatnot. That all gets turned into features. Features get turned into tensors. Tensors get turned into algorithms that turn into predictions. And eventually you have an actuator that goes out, and that whole thing is running and doing it a few billion times a second. And to debug that, it's highly complex. And we're looking for the entire suite of tools is largely missing in the market. I don't know if you see that, Peter. To deal with a tensor as a first principle item, like your data as we do for tools, tensor is a fundamental thing in these deep neural networks. For most people, the word tensor is also a foreign language. And that's kind of like a relation was in a database. And you have a set of tensors. Is that a stratified sample or not? I don't know. Is this a good tensor representation? I don't know. Are my tensors of the right dimension, and do the tensors match the algorithm I'm going to use? A lot of things are missing.
Yeah, I think that's right. Another thing is I think we're seeing more specialized sets of tests and criteria, right? So in the old days, it used to be, does your program crash, and does it make the results better? Okay, ship it. And now it's like, oh, well, yeah, you have to not crash. You have to make things better. But there's also a security review, and there's a privacy review, and there's a fairness review. And so all these issues that previously people weren't even thinking about are now part of the debugging and testing process.
That's a great point, Peter. We're seeing this a lot, like AI has become a real team sport. And we were just talking at Stanford about this, and it's a big theme inside Google today, is that now, because these are tools of thought for the first time, and now they're affecting how we make decisions that affect people, even more so than systems. And you're affecting people, what we're seeing is you also almost have to assume that your particular point of view is wrong. In the sense that, how do you have multiple points of view as this is making a decision that affects people's lives, people's credits, people's health, people's nature, their driving and autonomy and whatnot. So now we're figuring out what are the tools to make sure this is a relatively unbiased conclusion. Is this tool making a fair decision? Is this tool following the guidelines of where you want to apply it? Right? And there's a whole set of tools that I haven't really seen before in computer science that are now entering, because now we're entering areas of social science, of political science, of other areas where we have other systems that are human systems, but now we can have new autonomous systems. And that, to me, Ted, is a whole new raft of tools that are just now coming on the market.
And I think another issue we have is trying to project into the future. And when we build systems that rely on data, you can only rely on the data you have. I guess this is an area where we're different than being a scientist, right? Because as a scientist, you sort of observe nature, and you feel like, well, my observing it isn't going to change it all that much. But when you're
But you do use Newtonian physics to predict where things are going to fall, right?
But you know, when you're a big company and you say, well, we're going to make a change to our algorithm, then you realize that everybody else is going to respond to that, and tomorrow the data that you're going to get coming in is going to be different than today. So you can't just say, let's optimize for what happened in the past. You have to say, if I make this change, what will the future be like? And that's something that you don't have any data for because it hasn't happened yet. And so there you need actual understanding rather than just pumping the data in and seeing what comes out.
One of the things that a lot of the complex and big data systems that I've built in the past decade or two have been large symbolic knowledge bases or fact bases or text bases or whatever, things where they're analyzed. And one of the things that I often do with it is exploratory data analysis, essentially. I sit with a interpreter and I look for patterns, I test hypotheses, I do counting and look at distributions and things like that. And I think that that's one of the things that we also do with these numeric AI models. And I think that that's a big part, as Peter was saying, of the way that we do things, is that we're working with data and we're working with it to not just understand how the data fits what we're expecting, but also how it doesn't.
So actually, Scott brought back some complex memories for me. Well, actually, they're relevant, and they're relevant. It kind of goes to all this. When I look back at my time in the biological sciences, designing pharmaceuticals, and doing wet, this is not computational, doing wet chemistry, the tools we had were very limited for analyzing a system about which we know almost nothing, which was a guinea pig or a human being. And we would wick down the problem by just extracting it into a very small, taking a big problem, ignoring 99% of it, or 99.99% of it. And so I've got this compound, I want to inject it into this tissue, and I want to see it perfused in this particular fashion. Well, then you take a segment of tissue out of the guinea pig, you then extract from it a subset of the compounds that are in there. Now, you're aiming, of course, just to extract your own molecule, but really you're extracting a huge, messy subset that you're hoping is mostly not the stuff that you didn't want. Then, you run it through solvent, which is, of course, its own experimental problem, adds to the thing. And let's say you're doing chromatography and you run it through a chromatography column. And a chromatography column is this packed, literally a column of, say, charcoal. And molecules run through it and they stick to it for a while and then they release, depending on their molecular weight and some other properties. And you just run that and then you look at the spectrum and you're like, this should be my molecule because it's about this weight and there's about this much into it. And you hope that there isn't too much confounding data from those other crud. It's crud to us because that's not the stuff we're interested in. And out of that, we then make a determination that the compound is operating the way we want it to and blah, 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 blah. And honestly, these big dynamic numerical and symbolic systems are really no different from that anymore. Once your data set gets big enough, you really have no idea, but you're aiming for a particular result, and everything else is defined as noise or side effect. And I think that is probably, the pharmaceutical industry has been pretty successful, not what scientists would like, but makes people's life better. And in a way, that may be the best we can aim for today.
I'm a little less cynical. I
prefer to say realistic.
Okay, yeah, right. No, I remember when I first ran across some of the great tools for building the programs that we called AI back then, and you had DWIM. Well, DWIM was very simple, really. It was just find the variable.
DOM stands for do what I mean.
Yeah, that's right. But it really, you know, it was really just find the same variable everywhere, and master scope, you know, find the same function everywhere else that I hadn't thought of, and structure editors, make sure that I wrote it so that it was at least syntactically correct. And those things seemed so profound at the time. Now they're all built into Eclipse, but they do matter. I mean, these little things matter, and yet, you know, my first debugging experience that's worth talking about was when I was fixing televisions when I was a child. And there was this nice thing where you would take a screwdriver and you'd bang on a tube. And if there was signal going from there to the speaker or the screen, you would get something to happen, right? So you'd know that from there on, at least the path is functioning. And you'd go bang, 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 bang. And you know, you could do that in, you know, 3 seconds. You could tell where the problem was in the television. It's better than that though, because it's literally testing the whole path, the whole tool path from where you are to the output. And so you'd start at the output, and if nothing's coming out there, you've got to find another technique, right? But you know, even looking at the tubes, you see that it's glowing or not glowing. If it's not glowing, well, you know, no data is going through there. And I think that we still use things like this. I mean, I think back to Ken's examples, and you know, you just, I mean, nothing touches that code, you know, right? You know, I mean. Right.
I have another friend who also worked on fixing TVs and said the first thing to do is wipe down the screen and get all the dust off it, because even if you can't fix anything else, they'll say, wow, the picture's so much clearer. So maybe that's where we are today in some of our tools.
Oh my God. And with that,
the mic is dropped, right?
Yeah. So back to this parenting problem, which is, I think, you know, it's interesting as I listened to this parenting story that Scott was, that's literally, you know, we certainly, when we're parenting, have a representation and a goal for that child of what we want them to learn, how we want them to learn it, why we think it's important to learn. And I think that we aren't talking about the whole tools that we're using anymore. We have all of these things that, you know, this list of, you know, different things that are inside PyTorch or whatever. But actually, there's a whole another set of skills that are the parenting skills. And those, you know, we used to be explicit about representation. Now we just set up the experiment correctly. And that, you know, this experiment, we were describing experiments for the last 5 minutes. But where is the representation, and where can we get to, you know, in the world of talking about, explanation. So people used to say no representation without explanation. Now we're talking about explainable AI. Where are we going?
Is there a question in that, Ted?
Yeah.
Where are we going?
Where are we going?
Where are we going with representation? What will representation be like, you know, in 10 years, 5 years? What is it going to be all unwritten down like it is now? I mean, is it going to be you get a genetics guy to work on a genetics problem, and they know how to set up those machine learning things?
Maybe there's a couple thoughts. I think in the next decade, we're going to see, much like relations were with the databases, before there was an Oracle, before there was an MS SQL, IBM DB2, back in, was it 70s, 80s?
Relational databases.
Way back when. But the idea back, see, we're at a state where now we're all excited about relations and D trees and these cool representations and a high-level programming language and scripting, like it's called a database. And I think we're going to see that in the next decade with tensors. Because what I'm seeing now is more and more we're seeing representation as these tensors, and when a tensor flows through a computational graph, you're doing little multiplications and additions and nonlinearities, and you're composing these different graph structures to transform from one tensor to the next. And you reframe your problem as an optimization or a generation problem, and the computer's programming by figuring out what is that high-dimensional function to go from an input tensor to output tensor. And it's a general-purpose way to represent text, images, sound, and we're seeing more and more business, predictions, control. And I think tools to represent tensors will be as powerful as databases were, and there is no Oracle yet of the tensor world.
Still, I worry that that's maybe the alphabet, and there's probably a Strunk and White there's probably something about syntax or maybe even semantics that's going to maybe raise above that. Who knows?
So let me try to get at that by going over the history of machine translation. Right? So in the 70s and 80s, the approach was, well, we need good representations. And so we'll hire linguists, and they'll write grammars and dictionaries and so on, and they'll represent noun phrases and verb phrases and all those things. And it turned out that was really hard to do, because something like a noun phrase is much more vague than the types of objects that we put into our Java programs. And Fred Jelinek at IBM was leading the team there, says, this isn't working, and every time I fire a linguist, my scores go up. And so what he said was, rather than trying to have these complex representations, let's have our only representation be a word and a couple of words that came before it. So we had these n-gram models, and we just counted up and went from there, and that was state of the art right up into the 2000s. It got a little bit more complicated, but mostly it was just saying any structure, any representation you want to pull out is not going to be explicitly programmed in, but it's going to have to come as a side effect of saying, I'm looking at these number of previous words, and you were limited up to 5 if you had a personal computer and 7 if you had a supercomputer of how many words back you could look. But people realized that we're missing a lot of things, we're getting a lot of stuff wrong. And so then these sequence-to-sequence neural networks came in, where you said, rather than just saying, I'm going to look backwards 7 words, you say, you have the capability to look back infinitely far in the sentence, and the network is going to figure out what it wants to keep and what it wants to discard. And that seems to work better. But there's still a feeling that we're still missing something. We'd be better off if these systems better understood what a noun phrase and a verb phrase was, and what a subject of the sentence was, and so on. And so now we're trying to put some of those things back in. We're trying to rehire those linguists that we laid off in the 80s and say, can we combine the best of them with the best of these models that we already have?
I think one of the things with representation is to actually understand that representations serve purposes, and they actually serve a variety of purposes. And one of the ways that I look at any representation is that it's doing 3 things. It's doing selection, it's throwing a lot of stuff out. It's doing simplification, it's making some things simpler at the cost of making other things more complex. And it's providing imagination in that it's able to generate descriptions that you don't actually see there yet. So that a representation tells you about things that you haven't seen. Maybe it tells you things that aren't true about what you haven't seen, but in most cases it's able to do that. And I think understanding those features of representations makes a lot of sense for how we think about the representations in the systems, whether they're the features we design, whether they're the symbolic descriptions we use, whether they're the points of connection between different components or models that we train separately or partially together in these complicated systems.
Well, I'm strongly opinionated on this subject, and
Only this subject.
among others. And I think part of the issue is that the neural networks, the tensors themselves, are at the wrong level of abstraction for us to actually understand them in a useful way. And the example I might use is, well, I should say, so first of all, we need machines that are comprehensible to human beings. You can only debug a system you understand. And when we deal with other people, they may infuriate us for the reasons that Peter mentioned, but at least we understand them. And a lot of the failures of machines are because they surprise us. They lack that kind of common sense, which is both innate knowledge, shared knowledge, but actually shared knowledge on a shared structure that we understand. So you need ultimately symbolic systems that extract semantic understanding from those systems. And you're going to have to end up doing your debugging at that level, right? I mean, if I'm teaching a robot to paint a wall, I really want to say, take that brush and move it this way. No, 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 don't let that drip happen. adjust it down. I mean, that's how we teach a human being. And ultimately, these systems are going to be working on things so complex that you don't want to have to tell them, don't run over women walking bicycles across the street. They should inherently be able to infer that that's something you don't want. And that's not a syntactic phenomenon. And these neural networks are fundamentally syntactic operations. Even the translation systems that Peter talked about are in many ways fundamentally syntactic, and that's why they're so powerful with the limited computing power we have today, and yet so terrible. Right? They're really good for translating languages you understand already, as opposed to languages you don't. When they translate a language you don't know, you often get a really bizarre result back. And so my view is that in some ways, there's only so much effort that should really go into trying to debug at the neural network level. And that's true of our brains too, right? I really don't know what's going on in this 80 giganode machine I've got inside my head. I confabulate, we all have children, right? Why did you do that? Right? They don't know at the time. They confabulate a new explanation from principles that are extremely high level, and then they offer that to you, and they hope that that satisfies you. And ultimately, I think our machines are going to do that as well.
No, it's great. Any more to add to this?
By the way, I nominate you to come up with a new acronym to replace CRUD. It's going to have T for tensor in it.
T for tensor?
But it's going to have to be a great new acronym for instead of CRUD applications, right? CRUD applications, the work on databases, right? Read, update, So you're going to have to come up with the new one for tensors. That's going to be the metaphor everyone uses.
So I love interaction with groups, and I'm a little uncomfortable with it just being something you typed in from some anonymous place. We'll try that for a bit, but I want anybody to feel comfortable going to a microphone as well. There's one over there. There's one for Peter. That seems like maybe that's the most specific thing, so want to start with that?
Okay, will AI do better on data generated by machines instead of humans due to less bias and errors, industrial IoT over consumer IoT? Okay, that's a good question. So first thing is, never trust data where you ask humans something. Because as Gumby was just saying, they don't know what they think. So instead, if you want human data, get human data of observing them doing something rather than asking them. So I think that will help. But I also think you're right that the industrial is probably an easier place to go. And I think of the robotics industry, right, where, it's 2020. Where are our robots? I saw them on the Jetsons. Why don't we have them? And that's been true for the last couple of decades. And why are they slow to get here? And I think part of the reason is that home robots are really hard because everybody's house is different and the things they want them to do is different. And so, yeah, I can get a little disk that says it's a vacuum cleaner and let it run free in my home, but it can't do much of anything else. And there isn't really any other robots I can buy. But there are a lot of robots in industrial settings. And why is that? Well, there's a couple of reasons. One is their budget is higher, so they can afford to invest more in it. And the other is that their environment is more standardized. And so the robots can do better there. So I think that's definitely true, that in the next decade or so, you'll see a lot of those advances more specialized for a particular environment within one industrial industry, or maybe even within individual factories, rather than for the home consumer.
So I like this question because I think the answer is yes, for a slightly different reason. I don't know if the data are less biased or errorful, but they are certainly going to be more consistent and not going to change in the way that Peter mentioned that these guys have at Google. So you've got a system generating a easily characterized set of data with a known piece, and most critically has a known piece of behavior. I mean, remember the mechanical governor on an old steam engine? I don't know if you guys have seen it. It's two balls and a spring and two arms, right? And he uses angular momentum to regulate the control system. Now, in my car, when I had a car, you had an engine control system that reads a lot of sensors and whatever, but that governor, it operated perfectly, and it did a very complex computation that a human could not do but it operated in a way that was comprehensible to the human. And I think these systems are like that. In terms of being better than humans, the data are sometimes very messy. You get an unsafe condition in an oil refinery, you might need to shut it down. Well, you shut down an oil refinery, it's offline for 60 days. It's a very expensive downside. Of course, if you get it wrong, it explodes and kills everyone around you, right? And so those kinds of decisions are very difficult for people to make. The data flow that come from them are very highly characterized. And I think this is a great example of the kinds of place where AI systems that don't need to be as adaptable, even as a vacuum cleaner, will probably simplify the operation and improve a lot of economic value really rapidly.
So if you, that actually leads very quickly and easily into the subconscious question here. There's and bias. So there's this bias for not turning off the horizon and blowing up, causing lots of fish to die. What do you think about the difference between bias built into a system by its designer or learned by itself versus people? Yeah, there's a subconscious business here. What do you think of that?
I think that most of these numeric models, the neural models, they're basically all subconscious. And so whatever bias is in there, it's in there in a way more deeply than it could be in human judgment at all.
The problem is you're biased and I'm right. Now, everybody thinks that, right? That's the problem.
So I think part of the issue is deciding what it is that you're trying to solve for, right? And so you see examples where people argue not over the facts, but over what the goal is. So you take cases like ProRepublica did this investigation into a system that was trying to decide whether you should get out on parole or not. And so it gave defendants a score of how likely are you to recommit a crime. And they said, we have proof that our system is not biased, because if we give you a score of 6, you are 60% likely to recommit a crime, and that's equally true to within 1% or something, whether you're black or white, therefore we're not biased. And the critics said, okay, that's one metric that you're unbiased on, but here's another metric that if you make a mistake, who are you more likely to hurt? And they're twice as likely to hurt a black person than a white person. So they say, therefore, you are biased, right? And so there's no arguing over the data. It's arguing over what is it that we as a society value. And that's what the question is. It's not really a question of bias. It's a question of societal goals.
So there's if you look up cognitive bias codex on the web, you'll see 168 different kinds of biases that we all get to operate by. So I don't know, do we really have any concrete recommendations for debugging methodologies for professionals trying to use ML models and flow that tolerates stochasticity?
Randomness, right? So think about it. What we found, there's a wonderful invention now, was it 10 years old now, the Jupyter Notebooks? And I think the Jupyter Notebooks still have some bugs in them. There's observables trying to tackle that, and others are. But I think we use a lot of notebooks. It sure beats print statements. And now you've got the notion of you can reassemble a set of tests. And we're replete with notebooks. We have something called Colab. And we use that almost all the time to explore the data set. And we'll look over someone's shoulder and go, that's a cool exploration. It's a cool way to look at the data set. And we'll run notebooks as a way to test this and share. Instead of sharing a doc, we share in notebooks. You're sharing code, compute, as well as the document. And this is what Donald Knuth called literate programming. And it's an early form of literate programming. Sure, it has some bugs with state and others I think we'll go after. But I think that is an extraordinarily great improvement upon, I guess, print statements. And now you can actually put visualizations inside here as well. And that becomes a very powerful, practical tool for testing your data, running your data, and sharing a test, if you will.
So I have a lot of fun with the notebooks. I enjoyed them a lot. I think they do have some issues. So one is, like when we were playing with the list machine, it's possible to get into an inconsistent, unreproducible state, right? So if you evaluate this cell and then this one, and then you go back and reevaluate this one, now all bets are off. And so there are other systems, Streamlit.io is one, where you write your program once, and every time you make a change, it re-executes the whole thing from top to bottom, so you never get in that inconsistent state, but it has cached all the interesting stuff so it doesn't have to recompute them. And so I think there's still, we're in a stage where there's experimentation to figure out exactly what the right model is, but I think something like that is on the right path.
So the first time that I met Scott Penberthy, maybe it was the second, he said, check this out, as he changed T to nil on a list machine. And
that was fun.
And we watched the entire thing just collapse.
Smoke.
Into a pile of rubble. So that's a very simple experiment there.
But I mean, you get back to when those machines first came out. What's nice about that, they had ZMax. And in ZMax, you had a shell you could pop open and run right across your editor. You could do visualizations in the same language. You could do system programming in the same language. You can actually have access to the entire source code. You can debug in the stack, hit meta dot, and go directly to the source code for whatever you needed that was in the bug. Then you could patch it and run it on your own machine, right? We don't even have that today.
I actually run my debugger under Emacs so that I can write little subroutines in Emacs that will explore stuff in the debugger. It's more primitive, but basically Jupyter Notebook is just reinventing the list machine in some ways.
Ken has his microphone up in the upper position. So.
Well, I think that the thing with these notebooks is they're great for looking at the data, but there's still a question of how easily it gets confused. And I actually find Emacs gets confused more often than I like. But actually, just as context, how many people here know what a list machine is? Okay. In the late 70s and early 80s, there were machines that came out of the AI environments at primarily MIT and Xerox PARC that were machines that were designed from the top to run Lisp, which is an AI programming language. And in fact, the entire software stack, the window system, the scheduler, even the garbage collector, and the networking code were all written in Lisp. And it really made an amazing kind of environment for doing development, because I talked about deep stack stuff. Well, you could do all points in the stack in what was close to the same language. And it allowed you to create different kinds of applications.
So Ken, I got to interrupt you and ask you this. So think about Node.js, React.js, and we're seeing TensorFlow.js. I talked to the community in AI, like, no, it's going to be Python. But now you have like 9 million or so JavaScript developers. And now and if you have these new chips that are coming out, people say maybe this is the year of the chip. There's a lot of people now trying to figure out what these new chips are doing, matmul or approximate matmul. But that underneath Node, that's a bat out of hell. The thing really flies. So you think we're getting there with JavaScript?
I think we might be, because a lot of the underlying protocols are libraries which you access in JavaScript, and things are being written there. I think that when I've tried debugging a complex JavaScript implementation, if I've built something that uses it, it is just so easy to get lost in the layers upon layers of modules. Especially if it's a web-based thing, and you have
source code control, and you have editors online. You could do that as well, right?
Right.
Microsoft had one that made open source, and there's Emacs and whatnot. But now we're getting to the point where now you can actually prove that JavaScript is faster than C, because you can, the JIT can compile on the fly, and we're now seeing like serverless. Think of the next abstraction beyond containers are now doing OpenFAS, and you can actually turn a web call into a JavaScript function. And so one of the hottest things in IT now is you do everything in JavaScript, where your data center is your programming module, essentially. But it's JavaScript. And this sort of popped out as you're talking about list machine.
I don't like JavaScript, but
I didn't say I like it.
But there's a lot to be said for that, because JavaScript is part of a move to democratizing computing, democratizing programming, which I'm very much in favor of. And now you can compile it down directly into WebAssembly. You can write, in theory, I haven't seen it yet, but you could, in theory, write some pretty performant code. And another thing that I think we will see, just like SQL has become the database interface of abstraction of choice, forget the NoSQL databases, it's the database of choice. I think we may, instead of seeing the sort of massive NPM issue with 1 million libraries, we may actually just have 1 or 2, let's call them camps, where you get a single library, it's got soup to nuts for this class of problem, and it might have been ported to your whole data center or to run in your browser using the same programming interface, which I think will be JavaScript.
Have you seen ML5.js?
I have not.
Anyone here seen ML5?
Say what it say.
Okay, so there's a coding train. So it's Dan out at NYU on the other coast. And he has this thing called Coding Train. It looks like Thomas the Train for coders. It's kind of interesting. And we funded him. And the idea was take TensorFlow.js, and those team are working with them. And he has something called P5, processing. You folks play with processing? It's a language that's sort of built for creatives. And some beautiful artwork you can do with that, generative art. So he took processing, which is JavaScript-ish, and then you add TensorFlow.js, and then you have modules, and you have things like, for AI, that are kind of like pip, but for data sets. And it all sits and runs in a browser, kind of like CodePen.io, if you're playing with CodePen. And so the whole stack is there. And he takes the notion of embeddings and tensors and calculus and says, no, it's you can either get features or you get a prediction out of a model. And it's standard. And I saw that. And you see Observable now coming out, which is Observable is kind of like trying to go after the state problem by saying, let's make the whole document in JavaScript. Let's make it a truly reactive document. So now you blow up the state problem. But it's JavaScript. It doesn't have pandas, which everybody uses for data science, and doesn't have NumPy. But people are going after that now, too. So I don't know. It just sort of popped out in our discussion. So I'd encourage you guys to look at ML5.js. It's online. Super fun to play with. But it gives you a hint of maybe what's coming.
Okay. So I kind of, there's a question about, well, I guess I want to go back to, we've sunk down into the muck here with the tools at the very bottom. And I guess I want to make sure that people get a little to know each of you as much as possible. So if you want, you might want to, we can get back to these questions, but if you want, I'd be interested in saying a few words about something you're dreaming of doing now or are doing now that'll give people a feeling for you and the way you use tools today. What am I doing? I'm making a considerate conference calling system that uses AI to help people communicate better with each other, and I'm also using some machine learning in some medical work to make it easier for doctors to look at ultrasound and replace MRIs with ultrasound. So those are some things I'm doing.
At the end of this week, I'm handing in the 4th edition of my textbook. So this is the only event I'm doing this week other than that, and I only agreed to this because we were supposed to be done a month ago. And I guess some of what I'm thinking about is, so the book's going to be done, but what about all the supplemental material that goes with it? How do we actually teach students how to use AI and some of these tools and programs and workbooks and so on, thinking about how to put together the best collection of them, and whether it's going to be collecting things that are already there, creating stuff using the formats that are already available, or having to invent a new format. Because the great things about standards is everybody makes their own, right?
One thing that I've always been excited about, well, since for the last 20 years, has been part of the recent amazing breakthroughs, recent meaning 20 years, breakthroughs in AI have come from combining big data and big compute with these tensor-based decision models that are very old, it's an old tradition, artificial intelligence. And one of the things that I'm passionate about is coming up with ways to actually try to use symbolic methods with big compute and big data. And a lot of my focus has been on how do we actually do that? How do we manage a knowledge base with billions of cases? And that's what I'm really excited about. And last year, I open sourced, but haven't really tooted my horn about something called No, which is a framework for doing that. It's a runtime and a development environment and lots of other kinds of things.
Yeah, I had the URL up on it on the first slide, but find Ken.
Yep.
Find out more about it.
So what I've been working on for the past few years, and going back actually 30 years, is systems that can actually function with human beings. I mean, pretty much right now, the robots, like the robots Peter talked about, we put them in cages. We don't allow people to touch them. And the only, the AI systems that most people really interact with on a day-to-day basis may be a chat bot that they talk to for customer support, where the stakes are pretty low. If it sends you to the wrong FAQ, then you call a human being and you ask them. And I'm really interested in semantic systems that learn and behave the way people expect. Like the mechanical governor I was talking about. And the key to that, one of the keys to that is common sense. The other key to that is small data, not big data. I mean, big data is great, right? You get a huge, assuming it's clean, you get a huge set, and you can make a bunch of generalizations about that. But the fact is, we meet people every day, and we trust them to, if I hand this to Scott, he's not going to drop it or hit me over the head with it. I've never seen him before, but I saw him sitting at the table in the lunchroom. I kind of guess how long his arm is, and I do that. And we make decisions all the time. Someone comes to the door to repair to check your gas meter. How do you know who they are? Or you've seen them before. You don't have a huge database of every human being who works for PG&E. No, you have a set of heuristics you use, and you only need the information you need to solve the problem. I mean, I think these are problems concerning privacy and policy, and I think they're the problems that are what we really need to have things like self-driving cars or machines that we work. Like I said, no one is going to have a test case for a car of running someone over on a bicycle. So you have to have the machine know on its own that that's a bad idea.
Sure, but just a second. David doesn't just talk about this stuff. He always is writing programs about that.
Oh yeah, you can look my name up on YouTube, see a couple of YouTube videos. So
yeah, but
this.
Yeah. Every day you're laying down code about this.
Yeah, writing
What's the name of
C++
the system?
code. It's called Rodin, because of course he was the thinker, and that's what often is missing on these neural network systems. They're not really doing any thinking; they're just subconsciously reacting, to use Ken's analogy. And thinking is where I think all of the value is.
And just to push you a little further, how soon are people going to be able to play with Rodin?
I don't know, sometime next year. We have an older version. I had an older version at my last company that plays in a very restrictive blocks world, and I'm trying to expand that out.
They're hungry. You should feed them.
All right. Well, all right. We'll see.
I guess in the next decade, Ted, it's I almost like believe in magic, in the sense that when I was, 8 or 9, I saw this typewriter had this big old thing of paper in the back, and it was plugged in, and it made a lot of loud noises, and you could had a dial on it. You could dial up, and you dialed this machine built by a couple guys. I lived not too far from them, the HP garage, and you could type in one. It would say ready. You'd say 1, 0, and you punch these keys that are about an inch high, and you say print, and you'd print high, and you'd say 20 ends, and you do run, and the computer would come alive. It was magic to me. And that's why I fell in love with computers many years ago. And then I remember we had these, as a hobbyist, and we were playing with these Heathkit computers. It was so cool. And there was this jerk who wanted to sell the software. Because everybody knows you give the codes away to use the wonderful machines. And that jerk created this huge company in the Northwest. And it's now, he's one of the richest people, or depending who you talk to and how you evaluate holdings, he's the richest person in the world today. But along the way, was it who did the spreadsheet? Dan Brooklyn? Yeah. Suddenly, you could take this computing power that nerds like me could play with, and we were playing with Heathkit machines, and you could do a spreadsheet, and boom, took off. The whole PC generation. Now we're there with AI. the people who know how to do this well, there's 10,000 of them. And they all go to NeurIPS, right? This is a conference up in the Northwest. And they breathe mathematics. But you start seeing it where you can take 2 lines of JavaScript and you can recreate these models that were taken from years of research and run in your browser. That's magic. And I'm trying to think, how do you take the massive power of computing we have? Notebooks are part of it, JavaScript's part of it. We're not there yet. But Ted, I want to see, how can everybody in this room use AI and have that magic at their fingertips? Because I think only then will we as a human race really tap into what we have as a tool and use it. It's tool so powerful, we've got to get it out of the hands of the 10,000 and put it in the hands of the billion.
By the way, when I said next year, I forgot it's 2020, so later this year. Actually, you made me think of a couple of iconic tools, one of which is VisiCalc and now Excel, which took a lot of people who didn't think of themselves as programmers and had them write programs. It unlocked the power of the computer for people who did not see themselves as computationals, computing people. And the other one is HyperCard, which unlocked the Mac and really, and the web. And
let's talk about Siri.
And where, the sad story of Siri, I don't know.
Siri changed the world.
But I want to say, where's the tool? This is why I said about JavaScript. I don't like the JavaScript language, but I know a different way I'm fond of it because it's a democratizing tool. And I think that's really important that we have. That's why I want to make systems that people can understand, right? Because then people can actually use them. And maybe it's not Rodin, but it's some kind of hypercard, AI hypercard. It won't be the beefy tool that can ingest enormous amount of data. It won't be the library that's written by people with PhDs, but it will be the apotheosis of that ordinary people can use. And that's what I'm really looking forward to.
Cool. Well, do you want to say anything about about people writing, being able to write AI without having PhDs?
Yeah, I guess that's certainly a goal, and I think we're focusing on a lot of different levels. I like the spreadsheet analogy that you want to reach those types of people, and you want to. I think people will be programming at different levels, right? So you still have to have a good understanding of what you're doing in order to make a spreadsheet. But you talked about, like, Siri, what if we can have a conversation? And you can say, here's what I want, do this. And no, that's not quite it. And change that thing to be something else. So I'd like to get us to that level where you're even less of a programmer than a spreadsheet programmer.
Right. I mean, the bad news about Siri is it doesn't have shared state, it doesn't have context that you can set. It doesn't have a programming environment.
It has nothing to say.
Well, what is true is before Siri, conversational agents weren't viable, and now every company has them, and they are used by many, tens of millions of people all day long. So that is a demonstration of AI being accessible to many people. Unfortunately, we don't know how to train it and learn and have it learn.
Well, my problem with Siri, I think, is this apocryphal quote from Picasso, right? He said, computers are useless because they can only give you answers.
I know.
And that's really the problem. You can ask Siri a question, you get an answer back, but you can't, Siri doesn't understand you, and you can't actually have a conversation with her.
I'm sorry. So with that, I think we're going to wrap it up, and I don't know how long people are going to be around, if there's a break or not. There's no break, so we'll have to, you'll have to get hold of us however you want to, and thank you very much for listening.